Right now, at this very moment, there is something out there in the dark. It is not orbiting anything. It is not falling toward anything. It is not being pulled by anything strong enough to matter anymore. It is simply moving outward, away, into a silence so complete that the concept of silence barely covers it. It is a machine, built by human hands in human factories, from metals pulled out of the ground on a planet it will never see again. It weighs about 722 kilograms. It is roughly the size of a small car, and it has been travelling without stopping, without slowing, without any meaningful assistance from the universe around it for nearly 50 years. Its name is Voyager 1. As you watch this, Voyager 1 is approximately 23 billion kilometres from Earth. The signal it transmits, a whisper of radio energy, less powerful than a hearing aid battery, takes more than 21 hours to cross that distance and reach the 70-metre dish antennas we have pointed at the sky to listen for it. When we send a command, we wait 21 hours for it to arrive. Then we wait another 21 hours for any response. Every conversation we have ever had with Voyager 1 has been a conversation across days, and still, every day, it transmits, still moving, still measuring, still there. But to understand what Voyager 1 is, you have to go back to 1977, back to a world that looked at the sky and saw something it had never had the technology to reach, back to a group of scientists and engineers who realized they had a window, a brief, improbable, once-in-a-lifetime window, and decided, against enormous odds and institutional resistance, to go through it. This is not just the story of a spacecraft. It is the story of the furthest thing humanity has ever sent into the universe, and it is the story of what that thing is carrying, and what it means that we sent it at all. To understand why Voyager 1 exists, you have to understand the year it was built in. 1977 is not ancient history, but it is a different world. The Cold War is not background noise, it is the defining reality of every major decision made by every major government on Earth. The Soviet Union and the United States are locked in a competition that has extended by this binding point into orbit into the moon, and now, with increasing ambition, toward the outer planets. NASA had already achieved the impossible. 12 human beings had walked on the moon between 1969 and 1972. But the moon is close. The moon is, in cosmic terms, practically in the backyard. The outer planets, Jupiter, Saturn, Uranus, Neptune, are another matter entirely. Jupiter alone is more than 5 times further from the Sun than Earth. Neptune is 30 times further. Getting there with the technology of the 1970s meant journey times measured not in days but in years, and there was no guarantee you would get useful science out of it even if you made it. The instruments required to study the magnetic fields, particle environments, and atmospheric chemistry of the giant planets were pushing the absolute edge of what could be miniaturized and made to survive a decade in deep space. Nothing had ever operated that far from the Sun. No one truly knew what would happen. But in the late 1960s, a young aerospace engineer named Gary Flandro, working at NASA's Jet Propulsion Laboratory in Pasadena, California, made a calculation that changed everything. Flandro was studying the orbital mechanics of the outer planets and noticed something extraordinary. In the late 1970s, Jupiter, Saturn, Uranus, and Neptune would be arranged in a configuration that only occurs once every 176 years. In this alignment, a spacecraft launched from Earth could use the gravity of each planet to swing toward the next, gaining speed with each encounter, visiting all 4 outer planets on a single mission trajectory. This technique, called a gravity assist or gravitational slingshot, is elegant in a way that borders on beautiful. When a spacecraft passes near a planet, the planet's gravitational field accelerates it. If the trajectory is designed correctly, the spacecraft steals a tiny fraction of the planet's orbital momentum, an amount so small it has no measurable effect on a world as massive as Jupiter, but an amount that can double or triple the speed of a small spacecraft. You do not need fuel. You do not need engines. You need mathematics and timing. The window for the alignment Flandro identified would open in 1977. If they missed it, the next opportunity would not come until 2153, 176 years. Everyone who was alive to read about Flandro's calculation would be dead before another chance came. NASA immediately began planning what became known as the Grand Tour, an ambitious mission to send spacecraft past all 4 outer planets. It was, in the language of the people who designed it, a once-in-a-civilization opportunity. Then the budget was cut. In 1972, the original Grand Tour program was cancelled. The Nixon administration decided the full 4-planet mission was too expensive. What survived was a scaled-back version, 2 spacecraft, designed primarily to study Jupiter and Saturn, with the possibility of extended missions if they survived long enough. The spacecraft were named Voyager 1 and Voyager 2. It was not what the scientists had hoped for, but it was something. And in science, something is almost always enough to get started. The man who would spend the next several decades as the public face of the Voyager mission was Edward Stone, a physicist from Caltech, who became the project scientist for Voyager in 1972 and held that role for 45 years. Stone is, by every account, a man of extraordinary patience and precision, the kind of scientist who can explain the magnetosphere of Jupiter to a room of children and a room of Nobel laureates with equal clarity. He assembled a team of investigators across 11 different scientific disciplines. Each instrument on the spacecraft had its own principal investigator and its own team of scientists. They had to agree on priorities when priorities conflicted. They had to design instruments that could survive a decade of operation in an environment no instrument had ever operated in. They had to accept that when something went wrong, and things would go wrong, the spacecraft would be too far away for any physical repair. The engineers who built Voyager faced a specific and brutal constraint. They could not test it in the actual conditions it would operate in. You cannot put a spacecraft in a chamber that replicates the radiation environment around Jupiter. You cannot simulate a decade of cosmic ray bombardment in a laboratory. You design to the best specifications you have, you test what you can test, and then you let it go and hope that the engineering held. The power source alone was a masterpiece of pragmatic ingenuity. Solar panels, which power most spacecraft operating near Earth, are useless in the outer solar system. At Jupiter's distance, sunlight is 25 times weaker than at Earth. At Saturn, it is 90 times weaker. By the time you reach interstellar space, solar power is essentially zero. Instead, Voyager runs on nuclear decay. Its power comes from 3 radioisotope thermoelectric generators, RTGs, each containing pellets of plutonium-238. As the plutonium decays, it generates heat. That heat is converted directly into electricity through thermoelectric elements. No moving parts, no fuel tanks, no maintenance required. The plutonium simply decays, at a rate governed by physics rather than engineering, and will continue decaying for thousands of years. At launch, the RTGs produced approximately 470 watts of electrical power. That sounds modest. It is less than the power consumed by 5 standard light bulbs. But it was enough, carefully managed, to run every instrument, every transmitter, every heater that kept the electronics from freezing in the cold of deep space. The catch is that the plutonium decays at a fixed rate. Every year, the power output drops. By 2025, Voyager 1's RTGs were producing approximately 250 watts. That means that over the past 48 years, the spacecraft has lost nearly half its electrical power, and the engineers have had to make increasingly difficult decisions about which systems to keep running and which to switch off forever. But in 1977, all of that was in the future. In the summer of 1977, the spacecraft was ready. The window was open, and on September 5, 1977, launched atop a Titan I rocket from Cape Canaveral, Florida at 12:56 UTTC. Voyager 1 left the Earth. It would never come back. No one had ever planned for it to come back. From the first second of flight, Voyager 1 was on a one-way journey into the dark. The launch was not smooth. There were vibrations. There were moments where the telemetry looked uncertain. But the rocket performed. The trajectory was right. And within hours, Voyager 1 was already further from Earth than any human being had ever physically travelled. Ed Stone, watching the telemetry from JPL, later said that the launch felt like releasing something. Not just a spacecraft, something you had been holding on to for years, something you had built and worried over and argued about and corrected and recorrected. And now it was simply gone, out of your hands, into physics. The next thing it would encounter 18 months later was Jupiter. Before Voyager 1 arrives at Jupiter, we need to take a moment and understand what it actually is. Because this spacecraft is not just a vehicle, it is an engineering achievement so improbable that the people who built it are still to this day occasionally surprised that it works. Voyager 1 is built around a 10-sided aluminium framework. From the tip of its high-gain antenna dish, a 7-meter parabolic reflector that points back at Earth at all times, to the end of its science booms and magnetometer arms, the spacecraft extends across a volume roughly the size of a large family car. The high-gain antenna is the spine of the mission. Without it, everything else is irrelevant. It is the only way Voyager 1 can communicate with Earth, and keeping it pointed at the right place in the sky requires a 3-axis stabilization system that makes tiny adjustments, using small thrusters, constantly. Mounted on the spacecraft are instruments designed to measure nearly everything a spacecraft could measure in the outer solar system. There are 2 television cameras, actually Vidicon tube cameras, the technology of the era, that captured the images we still talk about today. There are ultraviolet and infrared spectrometers for studying atmospheric chemistry. There are magnetometers mounted on a 13-meter boom to keep them away from the magnetic interference of the spacecraft itself. There are instruments to measure the plasma environment, the charged particles streaming from the Sun and from the planet's magnetospheres. There is a cosmic ray subsystem that counts high-energy particles from outside the solar system. There is a plasma wave subsystem that measures electric and magnetic wave phenomena in the charged particle environments Voyager passes through. Every single one of these instruments was designed to operate for 4 years. That was the nominal mission duration. Jupiter and Saturn, and then mission complete. Voyager 1 is now approaching 50 years of operation. It has outlasted its design life by more than a factor of 10. And this is not because the engineers designed in margins they were not telling anyone about. It is because the spacecraft encountered an environment that in many ways was gentler than the worst-case scenarios, and because the team on Earth never stopped thinking of ways to extend its life. The most dramatic demonstration of that commitment happened in 2023. In late 2023, scientists monitoring Voyager 1's telemetry noticed that the data coming back from the spacecraft's flight data system was not making sense. The data was garbled, repeating a single pattern of ones and zeros that corresponded to nothing meaningful. The spacecraft appeared to be receiving commands from Earth correctly, and its instruments appeared to be functioning, but it was unable to format and transmit its science and engineering data in any usable way. The spacecraft was at this point more than 24 billion kilometers away. A signal took approximately 22.5 hours to reach it. Any troubleshooting cycle, send a command, wait for response took 45 hours, and the team was working with documentation, software, and hardware designs that were nearly 50 years old. Some of the original engineers had passed away, some had retired. The institutional knowledge of exactly why certain design choices were made existed only in paper files and in the memories of people in their 70s and 80s. The team spent months diagnosing the problem remotely. They eventually traced it to a single faulty chip in one of Voyager 1's 3 onboard computers, a chip that was corrupting the portion of code responsible for formatting science and engineering data for transmission. The chip could not be fixed, but the code could be moved. In April 2024, after months of careful work, the team sent a series of commands that relocated the affected code to a different region of the same computer's memory, spread across several separate locations that were not being used for anything else, with new pointers threading the sections together. Each command was sent across 24 billion kilometers of space. Each response took 22.5 hours to arrive. The engineers sent the fix and waited, as they have always waited, for physics to carry their words to the machine they built nearly half a century ago. It worked. In April and May of 2024, Voyager 1 began returning usable science and engineering data for the first time in months. All 4 remaining active instruments were confirmed operational. This is what the Voyager mission is. It is not just a spacecraft in the dark. It is a nearly 50-year collaboration between human engineers and a machine that has gone further than anything humanity has ever built. And that collaboration, against every reasonable expectation, continues. The team at JPL that monitors Voyager 1 today is small, a handful of engineers, most of them not born when the spacecraft launched. They communicate with it using NASA's Deep Space Network, a system of enormous radio telescope dishes at 3 locations around the world: Goldstone in California, Madrid in Spain, and Canberra in Australia. The 3 locations are chosen specifically to provide continuous coverage as Earth rotates. At any given moment, at least one of the dishes can see Voyager 1. The 70-meter dishes of the Deep Space Network are among the most sensitive radio receivers ever built. They have to be. The signal that Voyager 1 transmits, using a transmitter powered by approximately 22 watts, about the same as a refrigerator light bulb, is, by the time it crosses 23 billion kilometres of space and arrives at Earth, a trillion times weaker than it started. To detect it requires a dish the size of a football field, pointed with extraordinary precision, filtering out the noise of the entire universe to find the whisper of a specific spacecraft's heartbeat. The fact that we can hear it at all is, in its own way, as impressive as anything Voyager 1 has ever done. The engineers who maintain Voyager today operate in a discipline that has no real precedent. There is no handbook for maintaining a spacecraft 47 years old, operating at the edge of the solar system, built with components that are no longer manufactured, running software written in an assembly language that barely anyone alive still writes fluently. The engineers learn the mission the way you learn a language, by immersion, by reading old documents, by sitting with people who knew people who were there. Knowledge is passed in conversations, in annotated printouts, in the particular institutional memory that accumulates around a mission when everyone involved has decided, collectively, that the mission matters enough to keep going. There is something almost archaeological about the work when the 2023 to 2024 anomaly emerged. The corrupted data from the flight data system. The team had to go back to documentation from 1977. They had to read the original design specifications for a computer built nearly 50 years ago. They had to understand not just what the computer did, but why specific design choices were made. Choices made by engineers who are now dead or in their 80s. Choices whose rationale was sometimes not written down at all. Choices that had to be reverse engineered from the hardware itself. And they fixed it. Across 24 billion kilometres, with 45-hour round-trip communication delays, working from documents older than most of them, they diagnosed the fault, designed a solution, tested the solution as well as it could be tested from Earth, and uplinked the commands. And it worked. This is what is easy to miss when you focus on the spacecraft itself, that Voyager 1 is not just a machine. It is a relationship between a machine and the people who tend it. A relationship that has lasted nearly 50 years and has, despite every reasonable expectation, not yet ended, but the power is declining. By the late 2020s, the RTGs will no longer be producing enough power to run even the remaining active instruments. The team will have to shut down the last instrument. After that, Voyager will attempt to maintain its transmitter and its ability to communicate. But there will be nothing left to communicate other than, I am still here. And then, at some point in the early 2030s, the transmitter will fall below the threshold of detectability even for the Deep Space Network. The signal will disappear into the noise. The engineers will look at their screens, and the signal that has been there every day since September 5, 1977, will be gone. Voyager 1 will not know this has happened. It has no awareness of whether anyone is listening. It will continue moving, continue following the trajectory it was placed on in 1977, for billions of years, long after there is no one left to know it exists. But before we get to that silence, there is something bolted to this spacecraft that we have not discussed yet. Something that in many ways is more important than any of the instruments. Something that was not designed to measure the universe, but to speak to it. In 1977, Carl Sagan was 43 years old and already one of the most recognizable scientists in the world. He was an astronomer at Cornell University, a prolific author, a gifted communicator of science to the public, and a man of enormous intellectual ambition. He was also, in the words of colleagues, who loved and occasionally found him exhausting, constitutionally incapable of thinking small. When NASA approached him about contributing to the Voyager mission, Sagan did not think about instruments. He thought about legacy. He thought about what it would mean to send something out of the solar system, something that would drift through interstellar space for billions of years, potentially long after humanity had ceased to exist in any recognizable form, without putting something on it that said, "We were here, we thought, we felt, we reached." The result was the Voyager Golden Record. The record is a 12-inch gold-plated copper disc. It is mounted on the outside of both Voyager 1 and Voyager 2. It is designed to last in space for at least 1 billion years, possibly much longer, and it contains, encoded in the grooves of a physical medium older than electricity, a portrait of what it was to be human on Earth in 1977. Sagan assembled a small committee to decide what went on the record. The committee included Anne Druyan, who was the creative director of the project and who would later become Sagan's wife. It included Frank Drake, the astronomer who had designed the earlier Pioneer plaque, a simpler message on the Pioneer 10 and 11 spacecraft. It included Timothy Ferris, a music journalist, and several others with expertise in science, music, and linguistics. They had weeks, not months, weeks. The spacecraft were being prepared for launch and the record had to be finalized, pressed, gold-plated, mounted, and attached before the launch window closed. The committee worked at a pace that, by Anne Druyan's later account, bordered on the frantic and at times on the extraordinary. The music came first, and it was the most contested part of the record. The committee had roughly 90 minutes of total space on the disc for audio. They had to represent the full scope of human musical expression across cultures, centuries, and traditions. Every choice to include something was simultaneously a choice to exclude something else. They included Johann Sebastian Bach's Brandenburg Concerto No. 2, arguably the most formally perfect piece of music ever composed, precisely because it demonstrated human mathematics in sound. They included Chuck Berry's Johnny B. Good because it represented something different: joy, rhythm, electricity, the blues tradition that runs through the heart of American music. They included Blind Willie Johnson's Dark Was the Night, Cold Was the Ground, a wordless, aching guitar and voice performance from 1927 that Carl Sagan later described as one of the most profound pieces of music he had ever heard. They included court music from Java, panpipes from the Solomon Islands, a Pygmy girl's initiation song, Bulgarian folk music, a Navajo night chant, Azerbaijani folk music, a Peruvian wedding song, and a Beethoven string quartet. They included Louis Armstrong playing melancholy blues. They included a Japanese shakuhachi piece. They included 2 pieces from India. They included a Georgian choral piece whose harmonics, Sagan believed, would demonstrate to any sufficiently intelligent listener that humans understand the mathematical relationships between musical tones. The instructions for playing the record were engraved on its cover, along with a diagram of a stylus and turntable. The committee spent hours debating whether any non-human intelligence could actually work out how to use it. The answer they reached was maybe, which was enough. Then there were the greetings. The record contains spoken greetings in 55 human languages, from Sumerian, one of the oldest written languages on Earth, to Mandarin. The greetings were recorded by volunteers, sometimes in a single take, sometimes over several tries. They range from formal diplomatic messages to simple expressions of goodwill. In Amoy, a dialect of southern China, the greeting translates roughly as, "Friends of space, how are you all? Have you eaten yet? Come visit us if you have time." In English, the UN Secretary-General at the time, Kurt Waldheim, recorded a formal statement. And then there is the greeting recorded by a 6-year-old boy named Nick Sagan, Carl's son. His greeting in English is, "Hello from the children of planet Earth." That recording is now more than 23 billion kilometres from Earth. The boy who made it is now in his 50s. The images on the record, encoded as analog video signals that can be decoded using the instructions on the cover, include 115 photographs and diagrams. They show the solar system, mathematical and physical definitions, the structure of DNA, human anatomy, including images of a man and a pregnant woman, a nursing mother, people eating and drinking and working and running. They show the Great Wall of China, the Sydney Opera House, a sunset, a snow-capped mountain, a forest, the ocean. They show children, elderly people, people from dozens of different countries and ethnicities. They show a supermarket. They show a freeway interchange. They show a Jane Goodall photograph of a chimpanzee. There were arguments about the images. Sagan wanted to include a photograph showing a nude man and a nude woman, the kind of anatomical diagrams that had appeared on the Pioneer plaque, and that were, he argued, the most fundamental description of what a human body looks like. NASA was uncomfortable. There were concerns about how such images would play in the press. They compromised. The man and woman are shown, but the image was modified. Sagan considered this a failure of nerve. He may have been right. The most extraordinary item on the record is one that few people know about. In the days before the record's contents were finalized, Anne Druyan had an experience she would spend the rest of her life trying to describe accurately. She and Carl Sagan had fallen in love, suddenly, unexpectedly, in a phone call, in a moment of clarity she said came out of nowhere, and felt like the most real thing that had ever happened to her. They were not yet together publicly. They had simply, in that phone call, realized that they were going to be. The following day, Anne went to a laboratory at Bellevue Hospital in New York, where a neurologist fitted her with electrodes and recorded her brainwave activity while she meditated, while she attempted to compress into the activity of her neurons a sense of the full scope of what it means to be human, the joys, the sorrows, the connections, the loneliness, the love, the fear of death, the wonder at existence. Those brainwaves were encoded on the golden record. The brainwaves of a woman who had the day before fallen in love, brainwaves that she later said contained, among everything else, the feeling of having just fallen in love with Carl Sagan, are now travelling through interstellar space on a gold-plated disc attached to a machine that has gone further from Earth than anything humanity has ever built. Carl Sagan died in 1996. Anne Druyan still lives. The record still travels. The cover of the record also contains a map, a pulsar map. It uses 14 known pulsars, rapidly rotating neutron stars that emit beams, radiation at extremely precise, measurable frequencies, as reference points, with the Sun at the center. By measuring the frequencies of those pulsars and triangulating their positions, any sufficiently advanced intelligence that finds the record could, in theory, identify exactly which star the record came from. It is a return address for the solar system. Not everyone was comfortable with this. The physicist Freeman Dyson, among others, argued that broadcasting our location to a universe we know nothing about is the kind of thing that seems profound until you consider what might be listening. Sagan's counter was simple. The radio signals humanity has been broadcasting for a century have already announced our presence far more loudly than any spacecraft. If anyone is listening, they already know roughly where we are. The record is not a revelation, it is an introduction. There is something else to say about the golden record, something that sits underneath all the music and images and greetings. No one seriously expected it to be found. The probability of Voyager 1 coming within detection range of any intelligent civilization in the next billion years is, by any reasonable calculation, vanishingly small. Interstellar space is so vast, and the trajectories so slow relative to cosmic distances, that the record's journey is more likely to end in the heat death of the universe than in the hands of anyone who can read it. Sagan knew this, the committee knew this. They made the record anyway, because the record was never only for whoever might find it. The record was for us. It was an act of looking at ourselves, at every language, every song, every face, every heartbeat we chose to include, and saying, this is what we were, this is what we valued enough to send into eternity. Whatever else we did, whatever wars we fought and mistakes we made this. We looked at the universe and we tried to speak to it. That is what is bolted to the side of Voyager 1. That is what is travelling right now through interstellar space. Voyager 1 reached Jupiter in March 1979. 18 months of travel, 740 million kilometres, and nothing. No image, no photograph, no prior mission had prepared the scientists at JPL for what the spacecraft's cameras began sending back. Jupiter is not a large planet in the way that Earth is a large planet. Jupiter is a completely different category of object from anything in the inner solar system. It contains more than twice the mass of all the other planets in the solar system combined. You could fit 321 Earths inside its volume. Its equatorial diameter is 11 times larger than Earth's. Its magnetic field is 20,000 times stronger than Earth's. Its gravitational pull is so immense that it has spent the past 4.5 billion years acting as the solar system's primary shield, catching or deflecting the comets and asteroids that would otherwise have bombarded the inner planets far more frequently than they have. Jupiter is a gas giant, meaning it has no solid surface. What we see when we look at it is the top of an atmosphere that extends downward for thousands of kilometers, growing hotter and denser and stranger with depth, until eventually, at pressures so extreme they are difficult to generate in any laboratory, hydrogen becomes a liquid and then a metal, conducting electricity like copper wire. At the very center, there may be a rocky core roughly the size of Earth. No one has ever seen it, no one ever will. The atmosphere that Voyager 1 photographed in 1979 was a spectacle of organized chaos. Cloud bands stretch around the entire planet in parallel with the equator, driven by wind systems that have been in continuous operation for at least as long as humans have been watching. Within those bands, wind speeds reach up to 1,000 kilometers per hour. Storms rise and collapse and reorganize. The colors, the yellows, oranges, browns, and creams come from complex chemical compounds that form under the specific pressures and temperatures of Jupiter's upper atmosphere. And then there is the Great Red Spot. The Great Red Spot is a storm, a hurricane. But calling it a hurricane is like calling the Pacific Ocean a puddle. The Great Red Spot has been observed continuously since at least the 1830s, and there are sketches suggesting it may have been observed as far back as the 1600s. At the time of Voyager 1's encounter, it was roughly 25 kilometers across, more than twice the diameter of Earth. It is an anticyclonic storm, meaning it rotates in the opposite direction from the storms in its hemisphere, a consequence of the specific pressure gradients in Jupiter's atmosphere. It has been shrinking in recent decades. When Voyager saw it, it was enormous. Even now, reduced, it remains large enough to contain the Earth. But the Great Red Spot was not the biggest surprise Voyager 1 had at Jupiter. The biggest surprise was Io. Io is the innermost of Jupiter's 4 large moons. The Galilean moons, first observed by Galileo in 1610, it is roughly the size of Earth's moon. Before Voyager 1, it was expected to be a dead, cratered world, geologically inert. A navigation engineer named Linda Morabito, processing a routine navigation photograph of Io taken to calibrate the spacecraft's position, noticed something in the background of the image that should not have been there. A plume. Rising from the surface of Io like a curved umbrella, extending hundreds of kilometers above the horizon. Linda Morabito had, by accident, while doing routine navigation work, discovered the first active extraterrestrial volcano ever observed by humanity. Further analysis revealed that Io is not merely volcanically active, it is the most volcanically active body in the entire solar system. It has hundreds of active volcanoes. Some plumes rise 300 kilometers above the surface. The surface of Io is constantly being resurfaced, which is why, unlike every other rocky body in the outer solar system, it has almost no impact craters. Any crater that forms is quickly buried under fresh sulfur dioxide and silicate lava. The reason for this extraordinary activity is Jupiter's gravity. Io is in a gravitational tug-of-war between Jupiter and the other large Galilean moons. This creates a phenomenon called tidal heating. Jupiter's gravity stretches and squeezes Io as it orbits, flexing the interior of the moon the way you might flex a rubber ball. That flexing generates enormous amounts of heat, enough to maintain a partially molten interior and drive continuous volcanic eruptions. The surface temperature of the lava in some of Io's calderas exceeds 600 degrees Celsius. Next out from Io is Europa. Europa is covered in water ice, but it is not the ice itself that made scientists stop and stare at Voyager's images. It was the cracks. Europa's surface is smooth, almost entirely lacking the impact craters you would expect on a moon that old. It is crossed by a network of dark, reddish-brown lines, some hundreds of kilometres long. These lines are fractures in the ice, and the smoothness of the surface, combined with the fracture patterns, strongly suggested to the scientists studying the images that the ice was floating on something. That something subsequent analysis would confirm is a liquid water ocean. Beneath Europa's icy crust, perhaps 10 to 30 kilometres thick, there is an ocean of liquid salt water that may be up to 150 kilometres deep. Europa's ocean contains more liquid water than all of Earth's oceans combined. And where there is liquid water, with heat from tidal forces and chemical gradients from the interaction of water with a rocky seafloor, life cannot be automatically ruled out. Europa became, in the days after Voyager's flyby, one of the most scientifically compelling destinations in the solar system. It remains so. Ganymede, the largest moon in the solar system, larger than Mercury, showed complex terrain, ancient cratered regions alongside younger groove terrain, suggesting a geologically active past. Callisto, the outermost of the large moons, was heavily cratered, ancient and unchanged for billions of years, a preserved record of the early solar system written in ice and rock. Jupiter's magnetosphere was another revelation. It is the largest coherent structure in the solar system, extending more than 4 million kilometers toward the Sun and stretching as far as Saturn's orbit on the far side. Within it, charged particles are trapped and accelerated to enormous energies, creating radiation belts that dwarf Earth's Van Allen belts. If a human being stood on the surface of Io, the radiation from Jupiter's magnetosphere would deliver a lethal dose within minutes. Voyager's instruments, shielded and hardened against radiation, detected this environment directly, mapping a space more hostile than anything previously measured. After the encounter, Jupiter gave Voyager 1 what the mission needed most, a gravity assist. The spacecraft swung past Jupiter on a precisely calculated trajectory, and Jupiter's gravity accelerated it, bending its path outward and increasing its speed by approximately 35,700 kilometers per hour. Without the gravity assist, the journey to Saturn would have taken much longer. With it, Voyager 1 was on a fast track to the ringed planet and beyond. The scientific legacy of Voyager 1's Jupiter encounter extends far beyond what the spacecraft directly discovered. The questions it raised about the interior of Io, about the ocean beneath Europa, about the complexity of magnetospheric particle physics, drove decades of follow-up missions and theoretical work. The Galileo spacecraft, which arrived at Jupiter in 1995 and studied the Jovian system until 2003, was built largely to answer questions that Voyager 1 and Voyager 2 had posed. The Europa Clipper mission, launched in October 2024, is heading to Jupiter right now specifically to study the ocean that Voyager's cameras first suggested. The Juno spacecraft, which has been orbiting Jupiter since 2016, is mapping the planet's interior structure in a way that Voyager could not. All of it traces back, in a direct line of scientific inquiry, to the 18 months of data that Voyager 1 collected during its Jupiter flyby in 1979. This is how science actually works. Not in isolated discoveries that answer questions definitively, but in cascades, one observation leading to a question, the question leading to a mission, the mission leading to data, the data leading to new questions that the people who designed the original mission never thought to ask. Voyager 1 asked questions about Jupiter that we are still answering 45 years later, and the answers we are finding are more extraordinary than anything the original mission designers could have predicted. Linda Morabito, the engineer who noticed the volcanic plume on Io in a routine navigation image, did not set out to make a discovery. She was doing calibration work. She was processing images she had already looked at for a purpose that had nothing to do with science, when the universe handed her something that no human being had ever seen before. This happens in science more often than the textbooks suggest. The prepared mind encounters the unexpected thing and recognizes it for what it is. Morabito recognized it, And in doing so, she changed what we know about what a moon can be. Saturn appears, in Voyager 1's cameras, as a pale golden globe encircled by rings of almost impossible delicacy. No photograph, no painting, no description in any language quite captures the experience of seeing Saturn up close for the first time, which is perhaps why every scientist and engineer who has worked on missions to Saturn tends to reach for words like breathtaking and then stop, aware that the word is insufficient but unable to find one that isn't. Saturn is the second largest planet in the solar system. Its diameter is roughly 9 times Earth's, but its mass is much lower relative to its size than you might expect. Saturn is the least dense planet in the solar system. It is less dense than water. If you could find an ocean large enough to hold it, which would require an ocean larger than the solar system, Saturn would float. This extraordinary lightness is because Saturn, like Jupiter, is a gas giant composed primarily of hydrogen and helium. Its interior structure mirrors Jupiter's, a deep atmosphere transitioning to liquid metallic hydrogen at extreme pressures, with a possible rocky core buried beneath. Its storms and wind systems, while less visually dramatic than Jupiter's, are no less powerful. Wind speeds in Saturn's equatorial regions exceed 1,700 kilometres per hour, faster than anything measured at Jupiter. But it is the rings that Voyager 1 revealed in their full complexity, and it is the rings that remain one of the most structurally remarkable things in the solar system. From Earth, Saturn's rings look like a single continuous disk, with perhaps a few broad divisions visible through a good telescope. The most famous of these divisions, the Cassini division, a 800-kilometre-wide gap between the A and B rings, was thought to be simply empty space. Voyager 1's cameras revealed that the reality was infinitely more complex. The rings are not a few broad bands. They are a system of thousands of individual ringlets, each distinct, each maintained by a different combination of gravitational forces. Within the Cassini division, which from Earth appears to be a gap, Voyager found ringlets. Even the apparent gaps had structure. The rings are made primarily of water ice, chunks ranging in size from microscopic particles to boulders several meters across. They are extraordinarily thin relative to their width. The main ring system extends roughly 270,000 kilometers from the planet, but in most places is less than a kilometer thick. If you scaled Saturn's rings to the size of a football pitch, they would be thinner than a sheet of paper. What maintains this structure is gravity, specifically the gravitational influence of Saturn's many moons. Some moons, called shepherd moons, orbit at the edges of specific ring gaps and gravitationally herd the ring particles, preventing them from spreading. The F-ring, one of the most unusual structures in the solar system, is a narrow, twisted, braided ring maintained by 2 shepherd moons, Pandora and Prometheus, that orbit on either side of it. As these moons interact with the ring particles, they create knots, strands, and clumps that give the F-ring its complex, almost organic appearance. Voyager 1 also detected spokes, dark radial features crossing the rings that appeared and disappeared on timescales too fast to be explained by pure orbital mechanics. The spokes are now understood to be clouds of very fine particles levitated above the ring plane by electrostatic charging, essentially the rings generating static electricity that lifts dust into temporary structures. It is one of the strangest phenomena in the solar system, and Voyager 1 was the first spacecraft to see it. Saturn's moons yielded their own discoveries. Voyager 1 discovered 3 new moons during its flyby. It studied Rhea, Dione, Tethys, and Enceladus, finding surfaces shaped by impacts, by tidal forces, and by internal heat. Enceladus, in particular, had a surface that was surprisingly smooth and bright in some regions, suggesting that it was geologically young or still active. Later missions would show that Enceladus is venting plumes of water ice and organic molecules from a subsurface ocean, making it one of the most promising places in the solar system to look for life beyond Earth. And then there is the hexagon. At Saturn's North Pole, Voyager detected what later missions confirmed is one of the strangest structures in the solar system, a persistent hexagonal jet stream, a 6-sided atmospheric pattern, each side approximately 13,800 kilometers long, wider than the diameter of Earth. It has been continuously observed since Voyager first detected its signature in 1980. No one fully understands why it is hexagonal. Laboratory experiments with rotating fluids have produced hexagonal patterns under certain conditions, suggesting it may be a consequence of the specific rotation rate and atmospheric dynamics at Saturn's pole. But the mechanism is not fully settled. The hexagon rotates with the period of Saturn's interior, about 10 hours and 39 minutes, and the winds within it reach 320 kilometres per hour. It is a stable, persistent feature of a gas giant atmosphere, and it looks, in every image ever taken of it, like something that should not exist. But everything about Voyager 1's approach to Saturn was building toward a single decision, a decision that would define not just Voyager 1's trajectory, but the entire meaning of its mission. The target was Titan. Titan is not a moon the way our moon is a moon. Our moon is a barren, airless rock, geologically interesting, historically significant, but atmospherically silent. Titan is something else entirely. Titan is the second largest moon in the solar system, after Jupiter's Ganymede. It is larger than Mercury. It is larger than Pluto. If it orbited the Sun rather than Saturn, it would be classified as a planet. And unlike any other moon in the solar system, unlike any world except Earth and Venus, Titan has a dense, thick atmosphere. The atmosphere of Titan is dominated by nitrogen, approximately 98.4% nitrogen, compared to Earth's 78%. The remainder is mostly methane, with traces of hydrogen, ethane, acetylene, and a complex soup of organic compounds that form when sunlight and energetic particles from Saturn's magnetosphere break apart methane and nitrogen molecules in the upper atmosphere and reassemble the fragments into heavier compounds. This chemistry is called photochemistry, and on Titan, it operates on a scale that makes the chemistry of early Earth look simple. The result is a thick orange haze that completely obscures Titan's surface from above. Voyager 1's cameras, despite their sophistication, could not penetrate it. They photographed a featureless orange ball. Titan kept its secrets. What we know about Titan's surface comes primarily from later missions, specifically the Cassini spacecraft, which arrived at Saturn in 2004, and the Huygens probe, which separated from Cassini and descended through Titan's atmosphere on January 14, 2005. Huygens is one of the most extraordinary things humanity has ever done. It dropped through 100 kilometres of thick orange atmosphere, transmitting data all the way down, and landed on the surface of a world 1.2 billion kilometres from Earth. It transmitted from the surface for approximately 72 minutes before its battery died. What it found was a landscape of smooth, rounded cobblestones made of water ice, shaped by the flow of liquid methane, the way river stones on Earth are shaped by water. The surface pressure was 1.467 times that of Earth at sea level. The temperature was minus 179 degrees Celsius. The horizon, in the images Huygens sent back, showed a flat, dark plain beneath an orange sky, with cobblestones scattered across a surface that had the consistency, in the engineer's estimation, of wet sand. Titan's weather system is a methane cycle that mirrors Earth's water cycle almost exactly. Methane evaporates from the surface, rises into the atmosphere, condenses into clouds, and falls as methane rain. At the poles of Titan, there are lakes and seas of liquid methane and ethane, some of them larger than the Caspian Sea. One sea, Kraken Mare, is estimated to be approximately 400,000 square kilometres in area and possibly 300 metres deep. The complexity of Titan's chemistry is what makes it so scientifically compelling. The compounds that form in Titan's atmosphere, collectively called tholins, include organic molecules that, on Earth, are considered potential building blocks for the chemistry of life. Tholins are not alive, but they are the kind of chemistry that, on a world with liquid water and energy, might eventually lead to life. And this raises a question that no one has yet answered. Could life exist in liquid methane? Could a biochemistry exist that uses methane as its solvent the way Earth's biochemistry uses water? Theoretically, the answer is not obviously no. Methane is a liquid across a range of temperatures. It can dissolve organic compounds. It has properties that, while very different from water, might support certain kinds of chemical complexity. No one is claiming that Titan is inhabited. but no one can rule it out. And that is a profound statement about a moon orbiting a planet 2 billion kilometers away. For Voyager 1, the importance of Titan was not just scientific, it was navigational. To study Titan at the closest possible range, Voyager 1 had to fly through a trajectory that swung it below the plane of the solar system and sent it northward, away from the ecliptic. This trajectory meant that it could not go on to Uranus and Neptune. That task would fall to Voyager 2, which made different trajectory choices at Saturn and went on to become the only spacecraft ever to visit all 4 outer planets. Voyager 1's close approach to Titan in November 1980 was the last planetary encounter the spacecraft would ever have. After Titan, after Saturn, the mission became something different. The science continued. The instruments kept measuring, but the destinations were over. From this point forward, Voyager 1 was heading into the dark with no more ports of call, only the long, quiet journey toward the edge of everything the Sun had built. There is something worth dwelling on about the trajectory decision at Saturn. When the mission planners chose to send Voyager 1 through the Titan close approach trajectory, knowing that this would end any possibility of continuing to Uranus and Neptune, they were making a permanent choice with no possibility of revision. Once the spacecraft swung past Titan and was flung northward out of the ecliptic plane, that was it. The outer planets were closed. The die was cast. You cannot steer a spacecraft from 1.2 billion kilometers away quickly enough to undo a trajectory decision. The choice, once made, was made forever. This is the nature of exploration at interplanetary distances. Every decision is irreversible. Every trajectory choice closes doors that can never be reopened. The engineers and scientists who made those choices had to live with them, had to be certain enough in advance that what they were choosing to see was worth what they were choosing to sacrifice. In the case of Titan, the bet paid off. Titan turned out to be one of the most scientifically rich objects in the solar system. The close approach data from Voyager 1 was foundational to everything the Cassini-Huygens mission later discovered. But the decision was made without knowing that. It was made on the basis of what was known in 1980, not what would be known in 2005. The scientist who chose Titan chose it because Titan's thick atmosphere made it one of the most scientifically interesting objects accessible on the available trajectory, an atmosphere that was itself a mystery, opaque to their cameras, hiding a surface no one had ever seen. They chose the mystery over the known. They chose the closer unknown over the more distant known, and the mystery, when it was finally penetrated 25 years later by Cassini and Huygens, turned out to be more astonishing than anyone had imagined. Science at its best is like this. It is the willingness to choose the mystery. For a decade after the Saturn encounter, Voyager 1 travelled in silence. Its instruments measured the changing particle environment and magnetic fields of the outer solar system. The data came back day after day, year after year. The team at JPL monitored it. The signal delay grew longer. The power gradually declined. Carl Sagan had an idea. Sagan had been asking NASA for years to turn Voyager 1's camera back toward the inner solar system one final time. The camera be pointed away from the Sun for most of the mission. In the outer solar system, looking sunward risks damaging the sensitive Vidicon tubes by pointing them too close to the light source. And by 1990, Voyager 1 was so far away that photographing the planets would produce images of limited scientific value. The planets would be tiny points of light. Sagan argued that this was precisely the point. He wanted to show the Earth not as a world, not as a destination, not as the center of anything, but as it actually is from the perspective of the cosmos, a speck, a dot, he believed, and argued persistently, persuasively, over years, that this image would communicate something that no scientific data could. That seeing the Earth as one tiny point of light among billions would change the way people thought about the planet, about each other, about what is worth fighting for and what is not. NASA was reluctant. The camera would be used near the end of its operational life. The risk of damage to the instrument was real, and the scientific return would be minimal. The images would show nothing that wasn't already known. Science programs do not typically prioritize symbolic images, but Sagan persisted, and eventually NASA agreed. On February 14, 1990, Valentine's Day, with Voyager 1 at a distance of approximately 6.4 billion kilometres from the Sun, the spacecraft was commanded to turn its cameras toward the inner solar system. It took a mosaic of 60 individual photographs, capturing 6 of the then-known planets as points of light against the darkness of space. Earth appears in one of those photographs as a pale blue dot, occupying less than a single pixel. It is caught in a diffuse band of scattered sunlight, a sunbeam, that falls across that portion of the image, the entire world. Every person who ever lived, every city ever built, every war ever fought, every piece of music ever composed, every painting ever made, every scientific discovery, every act of love and cruelty and genius and foolishness in the history of our species, all of it contained in a fraction of a pixel of reflected light. Carl Sagan wrote about this photograph in his 1994 book, Pale Blue Dot. He described the Earth as a mote of dust suspended in a sunbeam. He wrote that our planet is a lonely speck in the great enveloping cosmic dark. He wrote that there is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. He wrote that whether we like it or not, for the moment the Earth is where we make our stand. The photograph was taken, the data was received, and then, on February 14, 1990, after the family portrait was complete, Voyager 1's cameras were turned off for the last time. The shutter closed. The systems were powered down. From that point forward, Voyager 1 was blind. It still is. It is still out there, still moving at 17 kilometers per second, still transmitting data about the particle environment and magnetic fields of the space it is crossing, but it can no longer see anything. The instrument that gave us the volcanic eruptions on Io, the rings of Saturn, the cracked ice of Europa, the orange haze of Titan, and the pale blue dot, that instrument is cold and dark and will never activate again. What Voyager 1 has now, in place of vision, is something older and more reliable. It has momentum, it has direction, it has a trajectory calculated in 1977 that will carry it outward at constant speed for longer than any of the people who calculated it could live to imagine. And it is heading for the edge of everything the Sun has ever owned. Most people, when they think about the boundary of the solar system, imagine a line, a fixed edge, clearly defined, beyond which the Sun's influence simply stops. The reality is more complex, more interesting, and far stranger. The Sun does not merely illuminate the solar system, it fills it. Constantly streaming outward from the Sun's corona is the solar wind, a continuous outflow of charged particles, primarily protons and electrons, that flows away from the Sun in all directions at speeds ranging from 400 to 900 kilometers per second. This solar wind does not stop at any arbitrary distance. It flows outward until it meets resistance, until the pressure of the interstellar medium, the thin gas and magnetic fields that fill the space between stars, pushes back hard enough to stop it. The region filled by solar wind is called the heliosphere. It is a vast, roughly spherical bubble, shaped somewhat by the Sun's motion through the galaxy and by the structure of the local interstellar medium. It encompasses all 8 planets, the Kuiper belt, and extends to distances of over 100 astronomical units from the Sun, more than 150 billion kilometers. Within the heliosphere, there are distinct layers. The first boundary Voyager encountered, after crossing the orbits of all 8 planets, after passing through the Kuiper belt, after decades of travel, was the termination shock. This is where the solar wind, which has been expanding and thinning as it flows outward, finally decelerates from supersonic to subsonic speeds. It is not a wall. It is a transition, a region where the behavior of the solar wind particles changes measurably. Scientists had models predicting where the termination shock would be. The models disagreed. Some placed it at 85 astronomical units. Some placed it at 75. Voyager 1 crossed the termination shock in December 2004 at approximately 94 astronomical units from the Sun, beyond the expected range. The heliosphere was larger than the models had predicted. Beyond the termination shock lies the heliosheath, a thick, turbulent region where the decelerated solar wind is compressed, heated, and mixed with particles from the interstellar medium. The heliosheath is not a quiet place. Voyager 1 spent 8 years crossing it. The magnetic field there is tangled and variable. The environment is in some respects more complex than either the clean solar wind inside the termination shock or the relatively steady interstellar medium beyond the heliopause. The heliopause is the final boundary. This is where solar wind pressure equals interstellar medium pressure, where the two environments are in equilibrium and beyond which the solar wind can no longer push. Beyond the heliopause, there is no more solar wind. There are only the particles and fields of interstellar space. The instruments on Voyager 1 could not directly photograph the heliopause. What they could measure was the particle environment, specifically the density of low-energy particles that originate inside the heliosphere and the density of high-energy galactic cosmic rays that originate outside it. Beyond the heliopause, the inside particles should disappear and the outside particles should increase. In the late summer of 2012, Voyager 1's instruments began registering exactly that pattern. The solar particles dropped, the cosmic rays spiked. The transition played out over several weeks of data, but it was unmistakable. On August 25, 2012, the scientific team at JPL concluded that Voyager 1 had crossed the heliopause. It was in interstellar space. Ed Stone, then 80 years old and still the project scientist, spoke to the press. He did not reach for dramatic language. He described what the instruments had shown, he explained what the data meant, and then he said, in a quiet voice, that Voyager 1 was the first human-made object to reach interstellar space. It had taken 35 years. The confirmation of Voyager 1's crossing into interstellar space was not, for most people outside the scientific community, a front-page moment. There was coverage. There were press conferences. Ed Stone spoke carefully and precisely about what the data showed, but the announcement competed, as scientific announcements always do, with everything else happening in the world in August 2012, and for most people it passed in a day or two and was forgotten. This is worth noting, not as a complaint, but as an observation about the relationship between human timescales and cosmic ones. The crossing of the heliopause by Voyager 1 was, in any objective sense, one of the most significant events in the history of human exploration. No human-made object had ever left the solar system before. No human-made object had ever entered interstellar space. This was a genuinely unprecedented category of achievement, and the world moved on in 48 hours. The scientists who had spent their careers waiting for this moment, who had built the instruments, analyzed the data, argued with each other about what the measurements meant, waited through years of ambiguous readings in the heliosheath. They understood what it meant. Ed Stone, who had been associated with the Voyager mission since 1972, who had watched the launches, who had been in the room for every major discovery, who had spent 40 years listening for a spacecraft that was now further away than anything human hands had ever reached. Ed Stone understood what it meant. He said it quietly, and it was enough. The data is what it is. The history is what it is. Voyager 1 crossed the heliopause on August 25, 2012. That fact will be true long after everyone who was alive to hear it announced has died. Voyager 2 would make its own crossing 6 years later, in November 2018, at a different point of the heliosphere, and the readings were different. Voyager 2 crossed at a point where the heliosphere appeared to be thinner. The heliopause was at a different distance, and the transition was sharper. This asymmetry in the heliosphere was itself a scientific discovery. The shape of the bubble around our solar system is not uniform. The side facing the direction of the sun's travel through the galaxy has a different structure from the side trailing behind it. We discovered this because we sent 2 spacecraft in 2 different directions 40 years ago and kept listening. There is a detail about the Grand Tour concept that is easy to miss, and that is worth dwelling on. Gary Flandreau did not discover the planetary alignment and immediately propose Voyager. He discovered the alignment and wrote a paper. The paper was read, ideas accumulated, proposals were drafted, committees met, engineers debated. Scientists argued about which instruments to include and which to leave off. Administrators looked at budgets and shook their heads, and then, sometimes, approved things anyway. The distance between a calculation on a piece of paper and a spacecraft on a launch pad is measured not in kilometres but in human decisions, human arguments, human compromises, and human determination. Thousands of people worked on what became the Voyager program. Most of them are unknown outside the small community of planetary scientists and aerospace engineers who know this history. Most of them will never be known at all. But without any single one of them, without the engineer who figured out how to mount the magnetometer boom in a way that would survive the vibration of launch, without the programmer who wrote the navigation software, without the technician who soldered the connections on the radio transmitter, Voyager 1 would not exist. This is true of all the great achievements of science and exploration. They are collective acts, assembled from the contributions of hundreds or thousands of individuals, most of whom received no credit and no fame. The spacecraft gets the name, the mission gets the story. But the mission is made of people, and the people made decisions, and the decisions accumulated into something that will outlast every one of them by billions of years. The scientists who built Voyager 1 are, almost all of them, dead. The engineers who launched it are mostly gone. Ed Stone, who served as project scientist for 45 years and became the human face of the mission, retired from that role in 2019. The team that maintains Voyager today is younger. Some of them learned about the spacecraft from the same television programs and textbooks that many viewers of this video learned from. They are keeping faith with something they inherited. They are maintaining a connection that predates them and will outlast them. This is what exploration looks like from the inside. Not the romance of the launch, not the spectacle of the planetary encounters, but the daily discipline of listening for a signal, interpreting data, filing reports, keeping systems alive, passing knowledge from one generation of engineers to the next. It is unglamorous work. It is essential work. And it is, in its own way, one of the most quietly heroic things a scientific institution has ever done. What is it like where Voyager 1 is right now? Imagine the darkest place you have ever been, a room with no light, no moon, no stars visible. Now imagine that darkness stretching in every direction, up, down, left, right, forward, back, for a distance so large that the word distance stops feeling meaningful. The nearest object of any significance is the Sun, behind you, at a distance of more than 23 billion kilometres. It is not completely dark from Voyager's position. The Sun is still the brightest object in the sky, brighter than any other star, a star you could identify as your own if you were looking at it with the right instruments. But it is small. It provides no warmth. It provides no meaningful illumination. The temperature around Voyager 1 is approximately minus 270 degrees Celsius, 3 degrees above absolute zero. At absolute zero, all thermal motion of atoms ceases completely. 3 degrees above that is a cold so profound that nothing in ordinary human experience provides an adequate analogy. The coldest place on Earth, in the depths of winter in Antarctica, is roughly 200 degrees warmer than the space surrounding Voyager 1. The particle environment is extraordinarily thin. The interstellar medium through which Voyager is travelling has a density of approximately 1 atoms per cubic centimetre. 1 atom, on average, for every 10 cubic centimetres of space. By the standards of any vacuum we can create on Earth, this is essentially perfect emptiness. And yet, by the standards of the space between galaxies, it is almost crowded. The interstellar medium in our part of the Milky Way is relatively dense. We live in a region called the local bubble, where supernova explosions in the past few million years have blown away much of the gas and dust, but where there is still enough material to be measurable. Voyager 1 is measuring this environment directly. Its plasma wave subsystem detects the density of electrons in the interstellar medium. Its magnetometer measures the magnetic field. The measurements have revealed something unexpected. The interstellar medium is not uniform. It has texture. There are regions of higher and lower electron density, ripples in the particle population, structures that the instruments were not specifically designed to detect, but are detecting anyway. Interstellar space is not featureless. It has its own complexity, its own story, written in variations of particle density and magnetic field orientation that tell us about the history of stellar explosions, and stellar winds in our neighborhood of the galaxy. Every day, the engineers at NASA's Deep Space Network point their dishes at the sky, at the precise coordinates where Voyager 1 should be, calculated from a trajectory refined over nearly 50 years. And listen, what they hear, after filtering out all the cosmic noise, is a signal so faint it barely registers, a carrier wave, modulated with data from the spacecraft's remaining instruments. The signal has been traveling for more than 21 hours before it arrives at the receiving dish. The data comes in slowly. Voyager's transmitter, limited by its diminishing power supply, now sends data at approximately 160 bits per second. A modern internet connection transmits millions of bits per second. But Voyager 1 is not sending photographs. It is sending numbers, raw measurements from its instruments. And those numbers tell us things about interstellar space that no other source of data can provide. No other human-made object has ever been here. No model, however sophisticated, can fully substitute for the direct measurement. This is the situation as you watch this. The spacecraft works, the signal arrives, the engineers listen, the science continues. But the power is running out. Each year, the RTGs produce approximately 4 fewer watts of electricity. Every watt matters. To manage this decline, the team has been turning off systems methodically. Heaters for instruments no longer essential, redundant backup systems, anything that can be shed without compromising the core mission of keeping some instruments running and the signal transmitting. The cosmic ray subsystem was shut down. The low-energy charge particle detector was shut down. The ultraviolet spectrometer went cold years ago. One by one, the instruments that explored the solar system have gone dark, their final readings already incorporated into the scientific literature, their physical components now cold and inert in the deep space cold. What remains are a small number of instruments still measuring the interstellar, medium still doing science, still sending data back from the most distant human-made object in existence. The current expectation is that Voyager 1 will be unable to operate any science instrument by approximately the early 2030s. Sometime around that point, depending on how carefully the power is managed, the last instrument will be shut down. After that, Voyager will attempt to maintain its transmitter and its attitude control. But there will be nothing left to measure. At some point in the early to mid-2030s, the transmitter will fall below the threshold that even the largest antennas can detect. From Earth, the end will not look dramatic. There will not be an explosion. There will not be a final message, no farewell, no ceremony. There will simply be a moment when the engineers look at their screens and the noise floor is where the signal used to be. And Voyager 1 will continue its journey, unchanged, unaware, into a silence that will last for billions of years. And now we have to talk about time, not human timescales, not the careers of engineers or the lifespans of institutions. We have to talk about the time of the universe itself, because Voyager 1's story, the part that places it in the context of everything else that exists, has barely begun. When Voyager 1 loses contact with Earth, when the signal finally fades and the last engineer closes the last file, the spacecraft will not stop. There is nothing to stop it. In the vacuum of interstellar space, there is no air resistance, no friction, no force acting on it in any direction strong enough to meaningfully alter its trajectory. It will continue moving at approximately 17 kilometres per second, the speed it has maintained for decades, for an extraordinarily long time. 40,000 years from now, Voyager 1 will make its closest approach to another star. The star is called Gliese 445. It is a red dwarf, located in the constellation Camelopardalis. It is a faint, cool, long-lived star, far less luminous than our Sun, far less massive, burning its hydrogen fuel at a fraction of the rate that a star like our Sun burns it. Red dwarfs like Gliese 445 have lifespans measured in trillions of years, not billions. They will still be burning long after every Sun-like star in the galaxy has exhausted its fuel and died. Voyager 1's closest approach to Gliese 445 will occur at a distance of approximately 1.7 light-years. That is approximately 16 trillion kilometres. Pause on that for a moment. 1.7 light-years. The closest approach between a human-made object and another star system, after 40,000 years of travel. will still leave them separated by 16 trillion kilometres. The distances involved in interstellar space are so large that even the phrase closest approach requires careful handling. Voyager 1 will not be near Gliese 445 in any sense that would be meaningful to a human observer. It will simply be less far away from it than it is from any other star at that moment. The question of what will be on Earth in 40,000 years is one that has no reliable answer. 40,000 years is approximately 4 times the length of recorded human history. The civilizations that existed 40,000 years before the present are not merely unfamiliar to us. They are essentially unknowable. We can dig up their tools, their bones, their art, fragments of their material existence. But their languages are gone. Their social structures are unrecoverable. Their beliefs, their fears, their dreams, gone. Everything that made them specifically human, as opposed to merely anatomically modern, has vanished without a trace beyond what stone and bone can carry. Whatever exists on Earth in 40,000 years will be similarly unrecoverable to whatever exists in 80,000 years. The pace of change is impossible to predict. Human civilization, in its current form, has existed for roughly 10,000 years, a fraction of 40,000. In 10,000 years, we went from small agricultural settlements to cities of 20 million people, from stone tools to nuclear weapons, from the ox-drawn plough to the space shuttle. The pace of change in the past century alone has been so rapid that a person from 1924 would find 2024 nearly incomprehensible. 40,000 years at any comparable pace of change is time enough for everything we are to become everything we cannot currently imagine. This is worth sitting with because it has a specific implication for Voyager 1. The spacecraft was launched by a civilization called the United States of America as part of a program called NASA, funded by a Congress that approved a budget, built by engineers working at institutions whose names we know, carrying a record chosen by a committee whose members we can name. In 40,000 years, the United States will not exist. NASA will not exist. The languages in which those names are written will not be spoken by anyone. The entire social and institutional context that produced Voyager 1 will have dissolved into history so remote that its details are completely unrecoverable, and Voyager 1 will still be there, still moving, still carrying its record. Having outlasted in its short 40,000-year journey every institution and every language and every nation that produced it. This is one of the most vertiginous aspects of thinking about Voyager 1's journey. The spacecraft is already, in a certain sense, beyond us. Not physically, it is still within reach of our radio signals, still within the computational reach of our orbital mechanics. But temporally, it belongs to a future that we will not see and cannot reliably predict. It is already a message from us to whoever comes after us, not just to whoever might find it in interstellar space, but to our own descendants, whoever and whatever they may be. Voyager 2, its sibling, launched just 16 days before Voyager 1 and now trailing it in a completely different direction through interstellar space, will make its own closest stellar approach in approximately 40,000 years, passing near the star Ross 248. The two spacecraft, launched within 2 weeks of each other from the same launch pad, will spend the next 40 millennia and beyond drifting away from each other, exploring different regions of the galaxy, each carrying an identical golden record, each transmitting its silence into the void. Think about what it means that they are out there. Two objects carrying the sounds and images and greetings of a civilization that will not exist in any recognizable form when they make their closest approaches to other stars. They are artifacts not just of technology, but of a particular moment in the history of a species, a moment when that species had just barely left its home planet, had just barely reached the outer planets of its own solar system, and had decided, against all probability of success, to reach further still. Millions of years pass, then hundreds of millions. The scale of the story changes so fundamentally that the human concepts we have been using, years, distances, the names of people and institutions, become inadequate. We need new frameworks. The Milky Way is a barred spiral galaxy approximately 100,000 light-years across and about 1,000 light-years thick At our location in the Orion Arm, it contains somewhere between 200 billion and 400 billion individual stars. The Sun sits approximately 26,000 light-years from the galactic center, orbiting it once every approximately 225 million years, a period sometimes called the galactic year. From a human perspective, the Milky Way looks static. From the perspective of geological time, it is in continuous motion. Stars orbit the galactic center. Gas clouds collapse into new stars. Old stars explode in supernovae, seeding the galaxy with the heavy elements that the next generation of stars and planets will be built from. At 17 kilometers per second, Voyager 1 would take approximately 7 billion years to cross the Milky Way, if it were travelling in a straight line, which it is not, because the galaxy's gravity bends everything over long enough timescales. In practice, Voyager 1's trajectory will curve on scales of hundreds of millions of years as it responds to the varying gravitational landscape of the galactic disk. By 500 million years from now, the solar system has changed. The Sun has been burning its hydrogen for this entire time and is slowly, over billions of years, growing slightly hotter and slightly more luminous. By about 500 million years from now, this increased luminosity will have disrupted the carbon cycle on Earth sufficiently to make complex land-based plant life difficult to sustain. Whatever lives on Earth in this era will be very different from anything alive today. Voyager 1, by this point, has left the local region of the galaxy entirely and is drifting through stellar populations that no one on Earth could identify with the naked eye. The stars around it have changed. The constellations, from Voyager's perspective, would be completely unrecognizable compared to the night sky of 1977. By 1 billion years from now, the Sun is noticeably more luminous. The increased heat is beginning to drive the loss of Earth's oceans. Water molecules are being split apart in the upper atmosphere by ultraviolet radiation, and the hydrogen escapes to space. Over tens of millions of years, this process is relentless. The Earth of 1 billion years from now may be losing the liquid water that has characterized its surface for its entire geological history. Whatever was on Earth that began as Homo sapiens has either gone extinct, migrated elsewhere, or evolved into something so different as to be unrecognizable to the people who built Voyager 1. Voyager 1 does not know any of this. It continues. The degenerate era is a term that cosmologists use with a certain clinical detachment, as if the end of all stellar light is simply a phase transition, a change of state, no more emotionally significant than water turning to ice. And in one sense they are right. It is a phase transition. It is what happens when the laws of physics are applied consistently over timescales long enough to exhaust every source of energy that those laws allow. But it is worth sitting with what it means. The degenerate era is a universe in which no star has burned for trillions of years. A universe in which the light that illuminated every planet that ever existed, including the light that drove the chemistry that produced every living thing that ever lived on any of them, has been cold for so long that the concept of starlight is as remote as the concept of the Big Bang is to us now. A universe populated by dark, cold spheres drifting in a darkness so complete that there is no horizon, no direction, no above or below, only the slow drift of matter through a space that has no features to navigate by. In this universe, Voyager 1 is one of the most complex objects still intact. The planets of the solar system may still exist as cold, airless rocks orbiting a white dwarf that provides no warmth and almost no light. The moons of Jupiter may still be there, Io, its volcanoes long cold, Europa, its ocean long frozen solid, Ganymede, Callisto, all of them dark and still. The golden record is mounted on Voyager 1, not on any of them. The only human artifact that may be further from the white dwarf that was once our Sun than any of the planets is Voyager 1 itself, drifting through the galactic dark at 17 kilometers per second, a speed that, on the timescale of the degenerate era, might as well be stationary. Nothing about this is sad in any cosmic accounting. Sadness requires someone to feel it. The universe does not grieve its own changes. It simply continues, as it always has, doing what the laws of physics require, as does Voyager 1. By 3 to 4 billion years from now, the Sun is approaching the end of the main sequence phase of its life. The hydrogen in the core is running out. The core contracts. The outer layers expand. The Sun is becoming a red giant, a transformed object whose outer layers will swell outward to engulf Mercury and Venus and possibly Earth. Whether Earth is literally engulfed or merely scorched depends on details of the Sun's mass loss rate, but either way, Earth's surface will be sterilized. Whatever has been on Earth for the past 4.5 billion years will cease. The outer planets, Jupiter, Saturn, Uranus, Neptune, will survive the Sun's red giant phase. Their orbits will change as the Sun loses mass, pushing them further out. The outer solar system will be reorganized, but the planets will persist. Voyager 1 will be somewhere in the galaxy, billions of kilometers from the solar system it came from, entirely unaffected by the death of the star it was launched from. The Sun will shed its outer layers in a beautiful expanding shell of gas and dust, a planetary nebula, visible from thousands of light-years away. At the center, the Sun's core will be exposed. A white dwarf roughly the size of Earth but containing most of the Sun's mass, radiating its stored heat into the darkness for billions of years to come. The solar system as we know it will be gone. In its place, a white dwarf, surrounded by the surviving outer planets in their new, larger orbits, ringed by a glowing cloud of expanding gas that was once the Sun's atmosphere. Voyager 1 will not see it. It will continue moving through the galaxy, carrying its record of sounds and images from a world that no longer exists, heading toward a future that has no name in any human language. The Sun's journey through the Milky Way over the course of its lifetime is itself a story of extraordinary distances. The Sun has completed approximately 20 galactic orbits since it formed 4.6 billion years ago. In each of those orbits, each galactic year of 225 million years, the Sun has passed through different regions of the galaxy, sometimes closer to the denser spiral arms, sometimes out in the quieter interarm regions. The local stellar neighborhood that we see when we look at the night sky has changed completely over these timescales. The stars that neighbored the solar system when the dinosaurs were alive are not the same stars that neighbor it now. The stars that neighbored it when the Earth first formed are nowhere near it today. This means that Voyager 1, over the billions of years it drifts through the galaxy, is not passing through a static environment. The galaxy it moves through is itself in motion, its stars orbiting, its gas clouds condensing and dispersing, its spiral arms slowly rotating, its central black hole occasionally flaring as it accretes material. Voyager 1 is a particle in a fluid that is itself in motion, and the motion of the fluid will eventually dominate the motion of the particle. Over sufficiently long timescales, the original direction and trajectory of Voyager 1, so carefully calculated and maintained during the mission, will be lost entirely in the gravitational noise of a billion years of galactic dynamics. The spacecraft that was aimed so precisely, that was tracked so carefully, that the engineers can tell you its position to within tens of kilometers at a distance of 23 billion kilometers, that same spacecraft will, in a billion years, be somewhere in the galaxy that no calculation made today can reliably predict, not because the physics changes, but because the initial conditions compound, error by tiny error, into uncertainty. The precision of 1977 is swallowed by the indifference of geological time, and still it moves, still carrying, still going. There is a galaxy approaching us. It has been approaching us for billions of years. It will continue approaching us for billions more. And eventually, in approximately 4.5 billion years from now, it will be here. The Andromeda Galaxy, also known by its catalogue designation M31, is the nearest large galaxy to the Milky Way. It is a spiral galaxy, roughly twice the size of the Milky Way, containing approximately 1 trillion stars. It sits approximately 2.537 million light-years away from us, and it is moving toward us at approximately 110 kilometers per second. The collision between the Andromeda Galaxy and the Milky Way is not a hypothesis. It is not a scenario. It is a confirmed future event determined by observations of Andromeda's motion relative to the Milky Way, measured with sufficient precision by the Hubble Space Telescope to establish beyond reasonable scientific doubt that the two galaxies are on a collision course. This sounds apocalyptic. It is worth being clear about what it actually means. A galaxy is not a solid object. It is a collection of stars, gas, dust, and dark matter held together by gravity with enormous amounts of empty space between everything. When two galaxies collide, the stars within them almost never actually collide with each other. The probability of any given star in the Milky Way directly impacting any given star in Andromeda is extraordinarily small. The stars are simply too small relative to the distances between them. What happens in a galaxy collision is not a catastrophe of direct impacts. It is a catastrophe of gravity. To understand the Andromeda collision, it helps to understand how astronomers determined that it is coming. Measuring the motion of a galaxy that is 2.537 million light-years away is not straightforward. The distance itself is so large that it takes light, the fastest thing in the universe, more than 2.5 million years to cross it. The galaxy appears as a smear of light in the sky, not as an object with a clearly defined edge moving against a fixed background. Measuring its velocity relative to us requires a technique called spectroscopy. When a light source is moving toward you, the light it emits is compressed, shifted toward the blue end of the spectrum. When it is moving away, the light is stretched, shifted toward the red end. By measuring how much the light from Andromeda is shifted, relative to what we would expect from a stationary source at its distance, astronomers can determine how fast it is approaching. The measurements are clear. Andromeda is approaching at approximately 110 kilometers per second along the line of sight, directly toward us. But the motion perpendicular to the line of sight was harder to measure because even at 110 kilometers per second, the sideways motion of a galaxy 537 million light-years away, is so small in angular terms that detecting it requires extremely precise measurements over very long time baselines. The Hubble Space Telescope provided those measurements. By comparing Hubble observations taken years apart, astronomers measured the minute shift in Andromeda's position on the sky. The conclusion: Andromeda is heading almost directly toward the Milky Way. The collision is essentially head-on. The galaxies will not graze each other. They will pass through each other, fall back together, and eventually merge. The merger will not produce a spiral galaxy. Spiral structure in galaxies is maintained by rotation, by the angular momentum of the gas and stars orbiting a common center. When two spiral galaxies collide, the angular momentum of each is partially cancelled by the other. The result, after the violent dynamics of the merger have settled, is typically an elliptical galaxy, a more amorphous, rounder structure with stars moving in random orbits rather than the orderly disk-like orbits of a spiral. Astronomers have observed many galaxy mergers in progress in the universe. The Hubble Space Telescope has photographed hundreds of them. Pairs of galaxies in various stages of collision and merger, their spiral arms stretched into tidal tails, new star formation blazing in the regions where their gas clouds are colliding. These images are among the most beautiful and unsettling things ever produced by science. Beautiful because they are extraordinary, unsettling because they are also our future. What we see in those images of distant merging galaxies is what our own galaxy will look like from the outside in 4.5 billion years. The tidal tails, the burst of star formation, the slow gravitational waltz. Our galaxy will be one of those smeared, stretched, beautiful catastrophes in the sky of some distant civilization, if any distant civilization still exists to observe it. From Voyager's location in the galactic disk, the Andromeda collision would be the most extraordinary visual spectacle in the history of the observable universe. If there were anything on Voyager capable of observing it, for billions of years, Andromeda's trillion stars would slowly grow brighter in the sky. The first signs would be subtle, the smearing of Andromeda's shape as the galaxy's gravity begins to affect each other at long range. Then, over millions of years, the sky would transform. Andromeda's stars would fill larger and larger portions of the visible sky. Tidal tails of stars from both galaxies would arc across the heavens. At the peak of the merger, the sky as seen from any point in either galaxy would be blazing with stellar light, not the familiar night sky, with individual points separated by dark, but a sky so dense with stars that darkness itself would become rare. And through all of this, through billions of years of galactic collision and merger and settling, Voyager 1 drifts, unseeing, unaware, carrying its record of Earth sounds through a sky that no longer looks like the sky it was launched under. The golden record is still attached. The gold plating may be pitted and eroded by billions of years of cosmic ray bombardment. The copper disk may be scarred, but it is almost certainly still there, still carrying in its grooves the sound of thunder over Earth's oceans, the sound of a mother speaking to a child, the sound of Chuck Berry's guitar. None of those things exist anymore, but the record of them does. We are now in territory that requires us to abandon the timescales of human civilization, of geological time, even of planetary and stellar evolution. We have been counting in billions of years. Now we must count in trillions. The universe is approximately 13.8 billion years old. 1 trillion years is approximately 72 times the current age of the universe. It is a number so large that any attempt to make it intuitive is doomed to partial failure. The human brain, evolved to track seasons and lifetimes and generations, does not have the architecture to genuinely feel the difference between 13 billion and 1 trillion. We can write the numbers, we can do the arithmetic. The visceral comprehension of what such a duration means is simply not available to us. Nevertheless, 1 trillion years from now, the universe is a profoundly different place. Stars have lifespans. The most massive stars, the blue supergiants that burn tens or hundreds of times more brightly than the sun, consume their fuel in millions of years. They live short, brilliant, violent lives and die in supernova explosions that briefly outshine entire galaxies. The sun is a middleweight star, expected to live for approximately 10 billion years total. Smaller stars, the red dwarfs, the M-class stars that are by far the most common stars in the galaxy, burn their fuel so slowly that they will last for trillions of years. The smallest red dwarfs have estimated lifespans of up to 10 trillion years. They are, by any measure, the dominant form of stellar life in the universe, dominant in number and dominant in duration. When every sun-like star in the universe has become a white dwarf, the red dwarfs will still be burning. They are the last lights in the long twilight of the stelliferous era. By 1 trillion years from now, all stars larger than the smallest red dwarfs have completed their life cycles. The sun-like stars have long since become white dwarfs, slowly cooling, slowly dimming, their light a memory of nuclear fusion that stopped billions of years ago. The massive stars exploded long ago, their remnants, the neutron stars and black holes that drift silently through the galaxy. The galaxy, what was once the Milky Way and Andromeda and is now their merged elliptical descendant, is populated primarily by red dwarfs and their remnants. New star formation has slowed dramatically. The remaining red dwarfs are burning the last large supplies of available hydrogen. By 10 trillion years from now, the last red dwarfs are dying. They do not explode in supernovae. They are too small for that. They simply exhaust their hydrogen and begin to cool and dim. Over billions of years, they transition from red dwarfs to white dwarfs, hot, dense, Earth-sized objects containing the compressed remains of a stellar core, radiating the heat of their formation slowly into the darkness. The night sky from any world that might exist in this era, 10 trillion years from now, is almost completely dark. The familiar canopy of stars that has illuminated every night sky on every inhabited world in the universe's history is gone. In its place, a sparse scattering of dim, reddish points, the last dying red dwarfs, growing dimmer every million years. Between them, the darkness is total. The universe has entered what cosmologists call the degenerate era. The age of stars, the stelliferous era, the long cosmic period during which hydrogen fusion powered the light of the universe, is over. White dwarfs cool slowly, extraordinarily slowly. A white dwarf produced from a sun-like star retains its heat for a period of time that exceeds the current age of the universe by many orders of magnitude. Eventually, in a time so long it makes the stelliferous era look brief, a white dwarf could cool to the temperature of its surroundings, becoming what cosmologists call a black dwarf, a cold, dark, inert sphere of degenerate matter, radiating nothing, invisible, continuing to exist purely because nothing is exerting enough force to change it. Here is a remarkable fact about black dwarfs. None exist yet. The universe is not old enough. No white dwarf in the history of the universe has yet had enough time to cool to the point of becoming a black dwarf. They are objects of the far future, the most distant observable future, because we cannot observe them. They have not happened yet. They are waiting for a universe that will take longer to produce them than the universe has currently existed. The physics of white dwarf cooling is itself a remarkable story. A white dwarf is not generating energy. It has no source of nuclear fuel left to burn. It is simply a sphere of degenerate matter held up against gravity, not by pressure from nuclear reactions, but by the quantum mechanical property of electrons called degeneracy pressure. Electrons, being fermions, cannot occupy the same quantum state. Pack enough electrons into a small enough space, and this quantum mechanical exclusion principle generates a pressure that can support the weight of a stellar remnant. The cooling of a white dwarf is thus purely a matter of radiation. The sphere radiates its stored thermal energy into space at a rate determined by its surface temperature and size. As it cools, the rate of energy loss slows, because cooler objects radiate less energy per unit area. This means the cooling curve is not linear. A white dwarf cools relatively quickly at first, and then more and more slowly as it approaches the temperature of the surrounding space. The last few degrees of cooling, from a few hundred Kelvin down to the temperature of the cosmic microwave background radiation, take longer than all the previous cooling combined. This is why no black dwarfs exist yet. The universe is not old enough for any white dwarf to have cooled to ambient temperature. The white dwarfs produced in the earliest stellar generations, the ones that formed from the first generation of stars, perhaps 13 billion years ago, are still hundreds of degrees warmer than the space surrounding them. They are cooling. They will cool, but the timescale is longer than the age of the universe, and will remain so for orders of magnitude longer. Somewhere in the galaxy, perhaps, a white dwarf formed from a star that once had planets. Perhaps one of those planets once had life. The life is gone. The planet may still be there, cold and dark in a new, larger orbit, and the white dwarf radiates its last heat into the dark, indifferent to everything that lived and died in the system it once warmed. Voyager 1, in the degenerate era, moves through a galaxy that no longer glows. It drifts through a darkness occasionally broken by the dim warmth of a dying white dwarf. An object that was once a star, now spending its last heat over timescales longer than the age of stars themselves. It continues. We must now confront a possibility that most people have never thought about, and that is arguably the most unsettling idea in all of physics. The atoms that make up Voyager 1, the aluminium of its frame, the copper of its record, the gold plating on its disk, are made of protons and neutrons in their nuclei and electrons orbiting them. The protons are the key. Protons are among the most stable particles we know of. They have been here since shortly after the Big Bang. The proton in your body has been a proton, unchanged, for approximately 13.8 billion years. But are protons truly stable? Do they last forever? Or do they, over sufficiently long timescales, eventually decay? The standard model of particle physics, the most successful and precisely tested theory in the history of science, does not predict proton decay. According to the standard model, a proton is simply stable. It does not decay. But the standard model is not the end of physics. There are theoretical frameworks, called grand unified theories, that attempt to unify the three forces of the standard model into a single framework. These theories make a different prediction. They predict that protons are not stable. They predict that protons decay slowly, incredibly slowly, but eventually into lighter particles. The theoretical framework that predicts proton decay is worth understanding in slightly more detail because it illuminates something profound about the structure of physics itself. The standard model of particle physics is built on a principle called gauge symmetry. This is a mathematical property of the equations that describe how particles interact, a property that means the equations look the same even when you make certain transformations. Gauge symmetries give rise to forces. The symmetry associated with electromagnetism gives rise to the photon, which carries the electromagnetic force. The symmetries associated with the strong and weak nuclear forces give rise to the gluons and W and Z bosons that carry those forces. Grand unified theories attempt to find a larger symmetry that contains all three of these as special cases, a single mathematical structure of which the standard model is a low-energy approximation. The analogy is like discovering that two rivers, which appear to be completely separate, actually come from the same source high in the mountains. If such a larger symmetry exists, it would have a consequence: new particles and new interactions between particles that were previously thought not to interact. In particular, quarks, the constituents of protons and neutrons, would be able to interact with leptons, electrons and their relatives, through a new force, mediated by new very massive particles, and through these interactions a proton could, very rarely, decay into a positron and a pion. The reason proton decay hasn't been observed yet, if JETs are correct, is that the new particles mediating the interaction are extremely massive. So massive that the interaction they mediate is extraordinarily suppressed at low energies. The rate of proton decay is so low that even watching 1030 protons for years might not produce a single event, which is why Super Kamiokandé's null result doesn't rule out proton decay. It just tells us the rate is lower than we could detect with 50,000 tons of water in a few decades. There is something philosophically important about this. Grand unified theories are, at their core, theories of completeness, theories that say the apparent diversity of forces and particles in nature has a common origin, a single underlying structure. Proton decay is a prediction of that completeness. If it occurs, it means that the stuff of the universe, the matter we are made of, the matter Voyager 1 is made of, is not permanent. It is a temporary arrangement of more fundamental things, stable for an extraordinarily long time, but not forever. And if the stuff of the universe is temporary, then nothing is truly permanent. Stars will die, galaxies will disperse, black holes will evaporate, and the atoms themselves will eventually dissolve back into the radiation from which they came. The universe will be thorough in its ending. It will leave nothing behind, not even the cold, dark remnants of matter. Just energy, spread infinitely thin across an infinitely expanded space, at a temperature so close to zero that the distinction between it and nothing at all becomes a question for philosophers. We have looked for proton decay. The experiment designed to search for it is called Super Kamiokande, located deep underground in the mountains of Japan. It is a cylindrical chamber containing 50,000 tons of ultra-pure water, lined with approximately 11,000 photomultiplier tubes so sensitive they can detect individual photons of light. If a proton in the water were to decay, it would produce a flash of light detectable by those tubes. Super Kamiokande has been running for decades. It has watched billions upon billions upon billions of protons. It has not detected a single proton decay. The experiment has placed a lower bound on the proton lifetime. Protons live at least 1,034 years before decaying. If proton decay is real, if protons do eventually dissolve into lighter particles, which then decay further, until the original matter has been converted entirely into radiation, then every atom in Voyager 1 would eventually be affected. One by one, proton by proton, timescales of 1034 to 1040 years or longer, the atoms of the aluminium frame would cease to be aluminium atoms. The gold plating would dissolve, not into liquid, but into the fundamental particles from which matter is woven. Every solid object in the universe, every planet, every remnant star, every grain of dust, every spacecraft would eventually disappear in this way. This is not certain. If proton decay does not occur, if protons are genuinely stable, then matter persists. The cold, dark remnants of stars and planets and spacecraft remain solid objects indefinitely, drifting through a universe growing ever colder and more diffuse, but physically intact. In that case, Voyager 1 might in some sense last forever. Physics has not yet decided which of these futures is real. We are still looking. There is a law of physics called the second law of thermodynamics. It states that in any closed system, entropy, disorder, the dispersal of energy into increasingly uniform distributions, always increases over time. Things do not spontaneously become more ordered. Hot things cool down when placed next to cold things. Fuel burns and becomes smoke and heat. Structures break down. The second law is not a suggestion. It is not a tendency. It is as close to an absolute rule as physics has. The universe is a closed system, and the second law applies to it. What this means on the longest timescales is that the universe is moving toward a state of maximum entropy, a state in which energy is perfectly, uniformly distributed across all of space, in which no region is hotter than any other, in which no energy gradients exist that could drive any process whatsoever. In this state, nothing happens. Not because anything is preventing things from happening, but because there is no thermodynamic difference between any two regions of space that could drive a process. This is called the heat death of the universe. The term heat is misleading. It does not mean the universe becomes hot. It means that heat, in the thermodynamic sense, can no longer flow from one place to another. The universe reaches a temperature extraordinarily close to absolute zero that is perfectly uniform everywhere. The concept of heat death is sometimes misunderstood as a dramatic ending, a moment, a catastrophe, a final event. It is not. Heat death is a process, not a moment. It is the gradual approach of the universe toward an equilibrium that it may never quite reach, because the mathematics of entropy in an expanding universe has subtleties that physicists are still working through. In a static universe, one that isn't expanding, heat death would be straightforward. Energy would distribute itself evenly, temperature would equalize everywhere, and all macroscopic processes would cease. But our universe is expanding, and in an expanding universe, the future is more complex. As the universe expands, the cosmic microwave background, the faint glow of radiation left over from the Big Bang, cools. It is currently at about 2.7 Kelvin. In the far future, as the universe expands by many orders of magnitude, this background radiation will cool to temperatures so close to absolute zero that they are effectively indistinguishable from it. The universe's background temperature approaches zero asymptotically, getting closer and closer but never quite reaching it. Meanwhile, Hawking radiation from black holes contributes its own tiny trickle of energy to the universe. As black holes evaporate, they release energy in the form of thermal radiation, a spectrum of particles at a very low temperature. For the last black holes, the ones taking tans and 87 years to evaporate, this radiation is at a temperature so far below the current cosmic microwave background that it barely registers, but it is there. And as those last black holes evaporate, they add their energy to the expanding void. What happens after all the black holes have evaporated depends on proton stability. If protons decay, then within a timescale of perhaps 1,040 years, all matter in the universe has decayed into radiation. The universe is then a gas of photons, neutrinos, and electrons and positrons, all at effectively zero temperature, expanding forever. This is sometimes called the photon epoch, a universe of light, with no structure, no complexity, no processes, just energy dispersed. If protons do not decay, then matter persists. The universe eventually consists of a sparse collection of black dwarfs, the cooled remnants of white dwarfs, along with neutron stars, isolated black holes that have evaporated to nothing, and drifting clouds of atoms. This matter is cold, inert, and dark. Occasional quantum tunneling events might, over unimaginably long timescales, cause some of this matter to rearrange itself into strange configurations. Some theorists have suggested that quantum processes might eventually convert black dwarfs into tiny black holes, or cause the matter of a neutron star to rearrange into iron, but these events, if they occur at all, happen on timescales of 10 100 years or longer. They are not stories, they are mathematical possibilities. The universe does not end. It simply becomes unable to do anything. It persists without process, without structure, without event, in a state as close to nothing as something can be without actually being nothing. This is the heat death, not a bang, not a crunch, not a dramatic finale, just the long, slow, inevitable cooling of everything into a uniformity so complete that the word silence doesn't cover it. Because silence implies the possibility of sound, and sound requires structure, and structure requires energy gradients, and those are gone. And somewhere in that uniform, cold, structureless dark, if matter has survived, if proton decay has not claimed it, is a small metal object, moving at 17 kilometres per second relative to a reference point that no longer has any meaning. carrying on its surface a gold-plated disk, and in the grooves of that disk, the sound of rain. When the last black hole in the universe has evaporated, somewhere around 10^{-100} years from now, what remains? If proton decay has not occurred, then the cold remnants of matter, black dwarfs, frozen planets, drifting dust, continue to exist. The universe is cold, dark, and effectively static. If proton decay has occurred, then nothing solid remains. The universe is a dilute gas of photons and neutrinos, expanding forever into a cold, dark void. Either way, there are no more stars. There is no more light. There is no more chemistry. There is no more biology. There is no more meaning, in any sense that requires a mind to recognize it. And somewhere in this darkness, if proton decay has not yet claimed it, if the gold and copper and aluminium still hold their form, there is a small metal object, still following a trajectory calculated in 1977, in a universe that has completely exhausted every process it was built to support. In the grooves of a disk on its surface, if anything could read them, are the sounds of a world that lived for 4 billion years. The sound of wind, the sound of surf, the sound of a mother and child, the sound of two people falling in love, the sound of a 6-year-old boy saying hello from the children of planet Earth. The disk does not know it carries these things. It does not know that the planet those sounds came from no longer exists. It does not know that the universe around it has reached its maximum entropy and that nothing further will happen. It simply continues, because there is nothing to stop it. There is a thought experiment that physicists sometimes discuss when they are being honest about the limits of what science can tell us. The thought experiment goes like this. If you could observe the universe from outside, from some vantage point that existed beyond space and time and the laws of physics as we know them, what would the history of the universe look like? Not the history as a sequence of events unfolding in time, but the history as a complete object, the way a novel is a complete object, even though its events unfold sequentially when you read it. What would you see? You would see, from that vantage point, a universe that begins in extraordinary complexity, the Big Bang, the first stars, the first galaxies, the formation of planets, the emergence of chemistry, the emergence of life. You would see the history of life on Earth as a thin film of complexity on a small rock, persisting for 4 billion years. You would see, within that thin film, the emergence of something that could look at the rest of the universe and ask questions about it. You would see that something build instruments and think thoughts and make music and fall in love and go to war and make mistakes and occasionally do something extraordinary. You would see it build a machine and launch it into space on a trajectory that would carry it out of the solar system and into the galaxy. And then, from that outside vantage point, you would see the universe return to simplicity, the stars going out one by one, the matter dissolving or freezing into stillness, the complexity unwinding back toward the uniform, featureless state from which it came, the entire history of life and thought and creation compressed into what would look, from outside, like a brief, improbable brightening in the long darkness, a flicker lasting a few billion years in a universe that will last for 10^{-100} years or longer. In that brief flicker, a small metal object was thrown outward from a small planet and has been moving ever since. It is still moving. It is the last trace of the flicker that is still going in the right direction, outward, away, toward whatever is next, carrying what it was given to carry. We built it to keep going. There is a detail about the final chapter of Voyager 1's operational life that is easy to overlook. When the last instrument shuts down and the transmitter falls below the threshold of detectability, the spacecraft will not know. It has no awareness of its own operational status in any meaningful sense. It has computers, and those computers run software, and the software monitors certain conditions and responds to certain inputs. But there is nothing in Voyager 1 that experiences the cessation of contact the way a person experiences the ending of a conversation. For Voyager 1, there is no ending. There is only the continuation of what has always been. The movement outward, the slow rotation of its attitude control system making tiny corrections, the residual heat of the RTGs warming the electronics that are still powered, the mathematics of its trajectory unfolding exactly as it has unfolded for 50 years. The ending is ours. The silence is ours. The spacecraft will not notice it, and so it does. Somewhere beyond the heliopause, beyond the reach of any signal we can send or receive, beyond the boundary of everything the sun has built. Voyager 1 moves through a darkness older than the solar system, carrying the sounds of a world that built it and let it go. It carries the brainwaves of a woman who fell in love. It carries the voice of a child. It carries the mathematics of Bach and the joy of Chuck Berry and the ache of blind Willie Johnson singing in the dark. It carries a map home in case anyone ever needs to find us. It carries everything we thought was worth sending into eternity, which is to say, it carries everything we thought was worth saving about ourselves. And it keeps going, as it was always going to keep going, into a future so remote that no word in any human language can contain it. The universe is very large, we are very small, and we threw something into the dark anyway. We always do. Come back to the present. Right now, as you watch this, Voyager 1 is approximately 23 billion kilometres from Earth. Its signal is arriving at the Deep Space Network antennas after a journey of more than 21 hours. The engineers are listening. The instruments are measuring. The spacecraft, nearly 50 years into a mission designed for 4, is still working. We know exactly where it is. We know exactly how fast it is moving. We know the direction it is heading, the rate at which its power is declining, the state of each of its remaining active instruments. We have not lost track of it for a single day in nearly half a century. And when we eventually do lose contact, when the signal finally fades, we will still know where it is. We can calculate its trajectory forward in time with excellent precision for thousands of years. It is just that where it is going, we cannot follow. Voyager 1 is the furthest thing humanity has ever sent into the universe. It is the first human-made object to enter interstellar space. All of this is true, and all of it is remarkable. But the thing that is most remarkable about Voyager 1 is not what it has achieved scientifically. The most remarkable thing about Voyager 1 is that it exists at all, that a species that had never left its home planet, that had only reached its own moon 8 years before Voyager 1's launch, that was in the middle of a Cold War with limited resources and competing priorities, that this species looked at a planetary alignment that would not recur for 176 years and decided to use it. There is a version of the Voyager story that focuses entirely on the science. It is a good version. It includes the discovery of Io's volcanoes, the revelation of Europa's hidden ocean, the full complexity of Saturn's rings, the measurement of the termination shock, the crossing of the heliopause, the data on interstellar electron density that Voyager's plasma wave subsystem continues to return today. It is a version of the story that would satisfy any scientist who wanted to know what was learned and what the knowledge cost and what it was worth. But there is another version of the story, and it is the one that matters more in the end. It is the version in which the science is not the point, in which the point is something harder to articulate and harder to argue for, something that scientists often resist articulating because science is supposed to be about what can be measured and demonstrated and falsified, not about what cannot. The other version of the Voyager story is about why humans do things like this. Why, in the middle of a Cold War, with hundreds of other priorities competing for the same budget, with no certainty that the instruments would survive, with no guarantee of scientific return sufficient to justify the cost, with a launch window that would not recur for 176 years, why did a group of people decide to use it? Why did they fight, through committees and budget cuts and institutional resistance, to build something and launch it and listen to it for decades? Why, when the mission was supposed to end after 4 years, did they keep going? Why, when the instruments started failing, did they find workarounds? Why, when a chip failed 23 billion kilometers away, did they spend months writing new software and uploading it one command at a time across a communication delay of 45 hours? The answer is not efficiency. It is not cost-effectiveness. It is not strategic national interest, although the Cold War context gave it political cover. The answer is something that is embarrassingly simple to state and genuinely difficult to justify by the metrics that institutions use to evaluate themselves. They did it because the alternative was not to know, and not knowing, when knowing is possible, is a kind of failure that some people find intolerable. This impulse, the refusal to accept ignorance when curiosity can be satisfied, is one of the defining characteristics of the species that built Voyager. It is not universal, not everyone feels it, but it has been present in human beings for as long as human beings have been identifiable as human beings. It drove the first people who crossed the land bridge into the Americas, following game herds into a continent no human had ever entered. It drove the Polynesian navigators who crossed the Pacific in outrigger canoes, reading the stars and the swells and the birds to find islands that existed only in inference and rumour. It drove the astronomers who pointed the first telescopes at the sky and saw moons orbiting Jupiter and understood, in that moment, that the universe was not arranged the way everyone had assumed. Voyager 1 is that impulse given its most extreme expression. It is the furthest reach of a species that has always reached. It carries the sounds and images of everything that species was. The music, the languages, the faces, the heartbeats, into a future and a distance that no member of that species will ever share. It is an act of pure reaching, stripped of any practical justification, persisting because the reaching itself is the point. When Voyager 1 finally goes silent, when the last signal fades and the last engineer closes the last file and the last dish is pointed somewhere else, there will be a moment, a brief moment, in which humanity will have, for the first time in its history, truly lost something, not in the sense of an accident or a failure, in the sense of completion. The mission will be over, the conversation will be done, and whatever Voyager 1 is after that, an artifact, a message in a bottle, a record of human existence placed in the care of physics, it will be beyond us in every sense that matters. It will be out there, in the dark, carrying everything we were, and it will keep going, as it was built to keep going, long after there is anyone left to know it is there, long after the sun is gone, long after the earth is gone, long after the Milky Way and Andromeda have merged and settled into their new elliptical form, long after the last red dwarf has cooled and the last black hole has evaporated and the universe has done everything it is capable of doing. It will be there, moving, carrying, in the grooves of a gold-plated disc, the sound of a child saying hello, in the dark, still going.